Good morning, everyone. Welcome back to another exciting day in mathematics. Whoop, whoop. How's everybody doing? Good? Yeah? All right, all right. So, warm-up 79 is on the screen, so hopefully that shouldn't take you long. See how you do with that. Copy and go. All right, let's see what we got. Number 1. I need a sum, difference, and product. Let's see. How about Rebecca? What'd you get for the sum? 22. 22 plus what? 2i. Hands if you got that. That is correct. How about difference? How about the difference? Jacob, M, difference. -8 plus 8i. Hands if you got that. That is correct. How about the product? What'd you get for the product, Jacob? A. You get that one? I'll come back to you. All right, let's go to number 2. And we'll leave this one for Jacob A. There you go. It's being recorded and uploaded on YouTube. Let's go. All right, number 2, solve. First of all, we set it equal to 0. There it is. And then, what method did you use? Tell your neighbor. Then I'm going to have Anthony enlighten us. Gonna be the one that saves me. Nothing wrong. All right, Anthony. D. What'd you get? X minus 6 and x plus 2, and all that equal to 0. So he factored -12, -4. Looks about right. -6 and 2. So what are my solutions? Solutions, Anthony. X equals 6 and x equals -2. Hands if you got that. That is correct. He used factoring. It did work. If it didn't work, then you would go to completing the square quadratic formula. All right, let's go to number 3. Number 3, it says, right, well, first graph f of x equals x squared. So by now, you guys should be experts at this, yes? Yes, there's a cube. All right, so -2, 4, 1, 2, 3, 4. -1, 1, 0, 0. 1, 1, 2, 4, and we're going to label that f of x, and then we're going to write our new transformation using a1, b1, h -4, and k5, so a1, b1, h -4, and k5. So to rewrite this is g of x equals 1 times f, parentheses 1 over 1x, -4 times the negative is +4 squared plus 5. Now, do we need to show the 1s anymore? No. So then my transformation rule should be g of x equals f of x plus 4 squared plus 5. So where are we going to move all these points to? Danny? 4 left and 5 up. So 4 left, 1, 2, 3, 4, and 5 up, 1, 2, 3, 4, 5. So my new transform function should be up here. Now notice that I didn't move all the points, but I'm kind of giving you where it's going to be at. Which point did I show you that I placed where it moved? Which point did I use? The vertex over here was what? 0, 0. The original was 0, 0. This one is at -4 what? 5, -4, 5. Now check this out. We said that it was going to move 4 to the left. That means to -4. And 5 up. And we said that that is H and K, just to refresh your memory, okay? Let's go to number 4. Solution for number 4, tell your neighbor, and then Danny's going to pass it to someone. Solution for number 4. Solution for number 4. All right? Anthony E. You said what? D? Okay. Anthony D, what'd you get? -3, -3. Cool. Solution. Remind your neighbor what this means, and then Anthony E is going to enlighten us. What does that mean? What does that mean, Anthony E? Mr. Apodaca heard that one. Intersects, my goodness, yes. That's where both lines, if I ask you to graph these, they're going to intersect at this point at -3, -3. Copy the agenda, please. Warm-up 79, complex numbers. Today we're moving on. Your home plate for tonight is electric circuits. Let's go. Oh, yeah, one of my favorite sections. Today's going to go a little faster than yesterday, so hopefully everybody go like this really quick. Bear with me. So like that we can get this on the road. Let's go. We got this. All right. Also, once you're done copying that, get a Cornell note and turn in last night's home plate on Canvas. Go to Canvas, turn that in, please. Last night's home plate was numbers 1 through 18. Was it a piece of cake last night? Yes? Remember? Basically, it was everything from the warm-up, right? Thank you, Mr. Q. You're welcome. I got you. Once again, warm-up 79, complex numbers. And today we're moving on and we're continuing with electric circuits. Today we're going to actually use more of the complex numbers within the electric circuit. Okay? All right? So tonight's home plate numbers 19 to 24. You're like, ooh, that's only 5 problems. Why is that, Mr. Q? Oh, yeah. Let's go. Copy this code, UDXNZ, UDXNZ. That gives you access to the play sheet for tonight, UDXNZ. All right? Give you some time to train your home plate and then get a Cornell note ready, please. Go. All right, we good? All right, here we go. I can define and compute complex numbers. I can define and compute complex numbers. So, with that said, remind your neighbor, what are complex numbers? See if they remember. What are complex numbers? What were complex numbers? Complex numbers are numbers that have what? One real and one imaginary. There they are, these are not, and so on and so forth. From there, I gave you guys some of these just to know what each component was. Then we did some of these for home play as well. We've been doing these for a couple weeks now on the warm-ups. So far, good transition, yes? All right, so let's crank it up. Yes, here we go. Yesterday, we left off with electric circuits. And we talked about that an electric circuit can be defined and can be written in such a form as the one on the right. However, the basic components of an electric circuit, we said, were resistor, inductor, and capacitor. Resistor, inductor, and capacitor. Are we there so far? All right. So, on your paper, one more time, copy this one on the top left and leave space to the right because we're going to need to write more stuff on the right side of that table. So copy it one more time, please. If you want to, whoop, sorry. If you want to shorthand this, on this one, just write symbol. And here, that's fine, circuit component. And next to resistor, I'm going to use the letter R. For inductor, I'm going to use the letter I. And for capacitor, I'm going to use the letter, very good, C. All right? All right. So, with that said, to crank it up a little bit more for those that are using your color pens, I'm going to use blue for resistor. I'm going to use red for inductor and green for capacitor. Blue for resistor, red for inductor, and C for capacitor. So what we're going to do next, guys, I'm going to give you an actual circuit. You're going to look at it, and I want you to label it. So you copy it on your paper, and I want you to label it just with a letter so that you know what each component is. Here we go. Copy that, example 4. It says label the electric circuit. So copy this. You're like, oh, snap. I know, snap is right. But we still haven't gotten to the last form. At the end, it's going to be, oh, snap. Oh, snap. I like that. Here we go. So, let's do this one together. Here we go, just for the sake of checking it out. So we have an electric circuit here. Everybody with me? All right. So anytime you see this, it means that volts are going in through there, which means current, but it's usually regulated in volts. Okay. However, with blue, tell your neighbor the resistor, which is the resistor. Label it R with blue, resistor. All right, show your neighbor really quick. Who labeled this one? R? Yes? All right. So therefore, from there, with red, we're going to label the inductor. I. Inductor. Label the inductor. All right. So you should label this one, yes? Is that correct? And of course, the last one should be what, everyone? C for capacitor. All right? Hands if you got that by yourself. All right. So let's see. I want to see what you did. Send me a picture, please. There's a screen. Not that I don't believe you're taking copious notes, but just to double check. All right. From there, here goes another one. Look up. Oh, snap. Copy that one, please. Example 4Q. Let's go. So copy that one. And then label all the components that you see with the proper initials. I'll give you some time. Well, let me help you get started with this one. I'm just going to label this one over here V for volts. That's where the voltage is going in. All right? I'll give you some. Help me out with this one. Jay, get us started. What do I label these two right here? Yes, so that's C and C. Hands if you got that. All right. What do we label this one in the center right here? Dom. I for inductor. Hands if you got that. That is correct. So that leaves us with these two, and this one that has some voltage. That's just to indicate that the same thing that happens here is happening over here. So the only thing you should label here would resistor, and resistor. Hands if you got that by yourself. All right. Next. Here goes another one. Don't copy that one. I'm going to send you the screen so you can label it on the screen. You don't have to copy this on your paper. Just label it on the screen. I'll give you some time. Go. All right, looks like the majority got it. All right, you guys remind me of me in kindergarten. Let's go. Did any of you break your radios when you were kids? Any of you? No? Some of us? Oh, my bad. Okay. In the past, you're going to see that in movies, there were these things like this, rectangular, that were called radios, where it has like some speakers in it, and then you can move a knob, and it moves. Anyways. Okay, Mr. and Miss Techies, wow. Anyways, here we go. So, I see most of you label this one resistor, capacitor, resistor, inductor, yes? And then some of you actually went and labeled this one voltage. Hands if you got that, yes? All right, look at this one. Let me send you the screen again, label that please. This is the last one, just to make sure, and I'm just giving you different views of how some of the diagrams can differ from one to the other, but they're pretty close. Bless you. All right. So, with that said, help me with this one, please. Brandon Doherty. What do I label what? Capacitor in the middle. Resistor on top. Inductor for the rest. How about over here? Yeah, for voltage. That's where the voltage is going in. Hands if you got something like that. From 1 to 5, how comfortable are you identifying all the components on the circuit? We got this, right? All right. So, with that said, here goes a quick intro to electronics. Write your utensils down, look up to the screen. In electronics, we have current. What does that mean, Mr. Q? Electricity. There's two types. There's alternating current, and there is direct current. So, for example, alternating current, pay attention to this one. If you go to an outlet, do you ever think about how you plug in your charger? Which way it goes? Some of you do, some of you don't. Some of you just go and plug it in whichever way it fits. That's why it's called alternating current, because if you plug it in one way or the other, it alternates. However, direct current, you cannot alternate. And what is that, Mr. Q? These are batteries. Anything with a battery, such as your cell phone. If you were to switch the positive and the negative on your cell phone, guess what's going to happen to your phone? It explodes. Vehicles, they have a 12-volt battery that when it's charging, when the car is on, it stays at 14.4 volts as it charges. But capacity is 12 all the way up to, I want to say, 15 volts. That's direct. There's one that's for positive and one that is negative. If you go and want to help somebody turn on their vehicle, giving them a jump with their battery, and if you alternate those, that might damage either your car or their car. So you got to be careful when you go help someone that positive goes to positive and negative goes to negative. That's why it's called direct. It has to be direct. So, dangerous voltage, I want to say, is AC, because cars, it's only 12 to 14 volts. From time to time, you get like little sparks from here and there, and sometimes you feel it. But if you do that on the wall is 120 volts. You're like, oh, snap. Yeah, snap is right. That's why, since we were kids, they told us not to put what? Like coins in there or whatever the case. Now, there's some that go up to 240 volts. That's when they have like dryers or bigger machinery and so on and so forth. Now, Impedance, I'm going to be speaking about impedance, is the amount of current that can flow through an electric circuit. For example, if I was to tell you that that door has an impedance of maybe top 5 people fitting at the same time through that door, that would be max. Is that correct? Could you fit less? Yes. Could you fit more than that? Probably not. That's what impedance means. It controls how much flow of electricity goes through there. Now, that is measured, and I'm going to be using this symbol a lot. Stay focused. It's known as ohm. Ohm. Look up, please. Bah. Ohm is a unit of measure that we're going to use, and they use the letter or the Greek letter omega. This is the letter that they use. And we're going to be using that for the electric circuits. So I'm introducing this just very simple. I don't want to get too into it, but if you have questions, ask me. I'm the expert at this, and I can convey more knowledge. Yeah, $100 an hour, and we'll go from there. So, right? Anyway, so with that said, electric circuits have their symbol, and each symbol, check this out, engineers were able to convert those values into numbers, which are real and imaginary, that combined become what? Complex numbers. That's what we've been using. So check this out. This is what it says. For a resistor, it represents a real number A. An inductor, it represents an imaginary number B greater than 0. And a capacitor represents an imaginary number B less than 0. What does that mean, Mr. Q? Well, let me give you in simple words what it means. So on your table, I want you to add one more column and just write the word representation. Representation. One more column to your table. Representation. So, in other words, whenever you see a resistor, look up. The first thing that you're going to think of is just a constant. A constant. What does that mean? A number without a variable. So anytime you see on the circuit a resistor, you know that it's just a number. Whenever you see an inductor, it's going to be a positive imaginary number. Let me repeat that again. Inductor is what? Positive imaginary. Which means the capacitor is going to be a what? A negative imaginary number. Let me repeat that again. Constant, positive imaginary, negative imaginary. All right? As soon as you copy that, send me a picture so I can see that you copied that on your paper. Bah. This next example, I'm going to do completely so like that your brain can absorb everything we've been doing and I've been talking about. Because this is where some of you start getting like, oh, snap. Yes, oh, snap is right. Here it goes. Writing utensils down, look up to the screen. You'll send me the picture at the end. I'll give you some time. Look up to the screen. Writing utensils down. Hands off the keyboards. Here it goes. So I gave you this table. So by now, if I was to give you a circuit, we can translate this into actual values, math values. So watch. What do I do first? Well, first, I would copy the circuit. Second, I will label it. Look at it. Tell your neighbor which one's the resistor, which one's the inductor, and which one is the capacitor. Jacob A, go. The one with the top one, yes. All right. Which means the inductor is number 3. Which means the capacitor is 5. And notice here, instead of being just voltage or 12 volts, this is how much? 120. That means they're talking about maybe a room in a house that has current, and they have those circuits in there. Now, check this out. Now, I'm going to translate this into numbers. Here we go. A resistor, we said it was just a number, real number. So what would it be? 4. Inductor, we said it's a positive what? Imaginary. So this would be 3I. Why? Because it's 3 ohms, so it's 3I. Which leaves us with a capacitor that is, say, negative imaginary. So this would be what? Negative 5I. So here goes the process one more time. You're going to copy the circuit, label it, make a table, and translate that into numbers. Yes? This was my example. I'm going to give you one for you to copy. Here we go. So copy this next one. Copy the table, and here's your, here's your circuit. Example 5. Label that example 5. Here's your circuit, and translate that. Copy and... All right, Brandon, Felix, after you copy this, you label each one, so tell me which one's which. Yeah. Resistor is 9. 7, the inductor. Capacitor is 10. Okay. So now I need values here. Pass someone so they can give me values. Martin, what do I write for resistor? For inductor? 7I. And capacitor? 10I. What are you missing though? Negative. That is correct. Remember, the capacitor is the only one that's a negative imaginary. Hands, have you got that by yourself? Okay. All right. So far, so good. From 1 to 5, how come to write you with that so far? 4, 5, 4, 5. Here goes another one. Don't copy this one. Look at it. Tell your neighbor which one is which, and I'm going to send you this to your screen so you can label it on the screen. There it is. Those of you that are following on YouTube, you can copy it and then just translate that over here to the table. Go. All right. Let's you help me with this one, Bree. Help me label it. 5 resistor. 8 is in the inductor. 7 capacitor. Okay. Hands, have you got that? All right. So help me fill this in, Bree. Go. Let's go. Hands, have you got that? All right. Ready for a little challenge? All right, here it goes. Copy that one really quick. Hurry up, hurry up, hurry up. All right. Help me label this, please. Laura, go. Which one's which? Choose the capacitor. So it's 3. 4 is the resistor. So it's 5. 7 the inductor. And of course over here our voltage. Okay, hands, have you got that? All right. Next, I need some values right here. Anthony, did we call it Anthony E already? We did? Okay, let's call him again. Anthony E. Here we go. Give me numbers. 9. Hands, if you agree with that. That is correct, because 4 plus 5 is 9. That is correct. Inductor, 7I. Capacitor, negative 5I. Hands, if you got that. That is correct. Okay, so that, we got that. From 1 to 5, look up to you with that. All right, which moves us to the next thing. Look up. Here goes the part that we need for this tonight's home play? Look up, please. Look up. So, I'm going to give you a formula. Don't write it down yet. And it looks like this. V equals I times Z, where I is the amps or the current, and Z is the impedance or the amount of current going through. Okay? So, voltage equals I times Z. So, this is what I want you to do. Example 6, copy the formula, copy this diagram, and copy this table underneath. This is going to be the last example. We got about 5 minutes, so start writing a little bit faster. So underneath the letter I have this value, the value of 24 plus 12I. 24 plus 12I is going to be my impedance, I'm sorry, my amps, and my impedance is the value that we give for each one of these. So, without skipping steps, help me with this one. Brandon Doherty, which one is which from our circuit? Top one's a resistor, inductor, capacitor. All right, so give me values for our impedance. Anthony D. Four. 3I. Negative 5I. Okay, so now that we have our values from our circuit, now we can actually use this formula for each of these in order to find the voltage. Okay, so here we go. I'm going to write the formula right here. V equals I times the impedance. So, in order to find the voltage for the resistor, how much voltage is going through there, I need to write, what is the impedance or the amps? 24 plus 12I. I'm going to multiply that times this impedance. What is the impedance? 4. So, distribute the voltage going through the resistor is 96 plus 48I. That's the voltage going through the resistor. Next, same formula, V equals, we write again the impedance. How much was the amps? 24 plus 12I. However, I'm sorry, the amps, there it is. And how much is the impedance for the inductor? 3I. Distribute. That gives me 3I times 24. That's 72I. Hold on. Let me just show you this really quick. 3I times 12, that's 36I squared. What do you notice at the end, guys, here? We need to do what? Substitute what? -1, so times that. So this is negative 36 plus 72I. That's the home play for tonight, guys. Enjoy your home play. See you guys tomorrow. Bye. Bye.